We have a great lineup of speakers for this part of, or this session today. I want to first start by introducing Cain from the University of Washington, who's part of the Synovec group. And today she's going to be speaking to us about uncovering the volatile profile of potato taste defect in roasted Arabica coffee using GCMS, GC, GCMS, and chemometrics.
All right, thank you, Kate, for that introduction. As said, my name is Cain. I'm a PhD candidate at the University of Washington with Rob Synovec, and I'm here to talk about kind of a continuation maybe of our brunch and coffee break. We're going to learn a little bit more about the flavor profile of coffee, and especially what causes some off flavors in our coffee aroma. So being from Seattle, Washington, we're really interested in coffee. So as this infographic shows, we have some of the highest Google searches for coffee. And that might be due to the fact that we are home to the original Starbucks, but we also have a lot of really great coffee roasters around. So we like to think that we know a thing or two about coffee, but really anyone in here can be the judge of coffee quality. And when we are enjoying that coffee drink that we get from either our local roaster or Starbucks, we're really judging its quality based upon its flavors and its aromas. So if we take a look at this flavor coffee wheel, we can see that coffee can kind of span a whole wide range of flavors and aromas. We can have really desirable aromas, so those would be things that have cocoa flavors, nutty or fruity flavors in our roasted coffee beans. Or we can also get undesirable aromas in our coffee beans. So this would be things that would be like a very sour, fermented smell, or even a vegetable-like aroma. The main reason why we can get this really wide range of coffee flavors is due to the fact that coffee is a very complex matrix. So roasted coffee can contain hundreds to thousands of compounds with a really wide range of chemical classes. So for example, we can have thiols, we can have aldehydes, and even pyrazines. That chemical composition of coffee is really dependent upon the pre-harvest agricultural variables of how it was grown, what were the conditions, the climate, but also the post-harvest processing. So how long was it fermented? What was that fermentation process? And also what was the roasting conditions? So you can imagine that if you have defective coffee beans, those that might be moldy, insect damage, or over-fermented, that's going to produce those off flavors, those undesirable aromas in your coffee beans. So today I want to talk about one type of flavor defect that can affect roasted coffee beans, and that's known as potato taste defect. This is a sporadic flavor defect that affects coffee in the African Great Lakes region, so areas such as Uganda, Rwanda, and Burundi. And it's been linked to the presence of this intestia bug that basically feeds upon the coffee fruit as it's being grown. And it ultimately contributes this flavor of dirty potato, as the name implies, in both green and roasted coffee beans. It's been said that this is due to a molecule known as 2-isopropyl 3-methoxypyrazine, or IPMP for short. But what's really important to notice is that there's really not a correlation link between how the intestia bug feeds upon the coffee fruit and why we're getting this presence of that IPMP molecule. So in our preliminary study, we took sorted coffee beans that were sorted based upon their aroma. So we had clean coffee samples, meaning that they had no off aroma. And then we had mild, medium, and strong potato taste defect samples from this Great Lakes region. And we ran a targeted analysis of IPMP just using one-dimensional GCMS. And what we found was that the concentration of IPMP increased it as the strength of odor attributed to potato taste defect also increases, as the box and whiskers plot shows you on the right-hand side. This was a statistical difference in between odor attributions of IPMP concentration. So this is really great. We were able to say that IPMP is correlated to odor severity of potato taste defect. But then we got to wondering, well, if potato taste defect is affecting IPMP, it's most likely affecting other volatiles in the headspace of roasted coffee beans. So to fully characterize that volatile profile of potato taste defect, we decided to switch gears completely and move to comprehensive two-dimensional gas chromatography with time-of-flight mass spectrometry, and also chemometrics. The main reason why we switch from a 1D to 2D method is mainly because we get that increased peak capacity and increased detection sensitivity, so we can measure all the volatiles present in roasted coffee. So here I show 2 tick chromatograms of our roasted coffee beans. On the left-hand side is going to be one of our clean coffee samples that have no off-odor. And on the right-hand side is one of our coffee samples that has a strong potato taste defect odor as sorted by the sensory panel. So if we look at these 2 chromatograms, we can really see the complexity of the coffee matrix. And we have over 500 peaks detected in the tick chromatogram alone. But as Professor Synovec said earlier, the number of peaks in your tick does not equal the number of components actually in your sample. It's much greater than that. What's also really important to notice here is I have these 2 tick chromatograms plotted on the same color scale. So visually comparing these 2 chromatograms, we can see that the strong potato taste defect sample has less overall signal, which suggests that maybe a lot of our analytes kind of drop out in signal with the strong potato taste defect samples. So let's zoom in to kind of a region of our chromatogram of interest. And we can start to kind of make some identifications of some analytes and look at their signals between the clean and the strong sample. So in the pink oval, I've outlined IPMP. That's the one analyte that we know is definitely attributed to potato taste defect. And we can see that's not present in the clean coffee samples, but is present in our strong potato taste defect sample. I also label a couple other analytes that have positive sensory characteristics. So 2-ethyl-6-methylpyrazine, 2,3-diethylpyrazine, and linalool. These all have either nutty, roasted, or fruity aromas. And we can see that their signal is stronger in the clean coffee sample, as given by the red signal in the middle of their peaks, compared to the strong potato taste defect samples, where they start to kind of lose out on their signal. Now, I can go all day and take looks at every single one of these peaks visually and try to figure out which ones are stronger in the clean and which ones are stronger in the potato taste defect. But that's a lot of really fine differences to do, and I don't want to spend my entire PhD doing that, trying to mainly identify and quantify these samples. So instead, we decided to try to rethink, like, what are our chemometric tools that we can use to discover these chemically relevant differences between 2 or more samples. And we decided to turn to our tried and true tile-based Fisher ratio or F ratio analysis. As given again in Professor Synovec's talk, this is a supervised, non-targeted method that discovers analytes that are statistically different in concentration between sample classes. And it's based upon this F ratio metric that is basically the between class variance divided by the pooled within class variance. So analytes that are more likely to be statistically different will have a very high between class variance relative to their within class variance. So for tile-based F ratio analysis, we decided to take all of our clean coffee chromatograms and all of our strong potato taste defect coffee chromatograms, put them into the algorithm, which uses a 4-grid tiling system to ensure that we accurately capture the peak signal for each one of our peaks in our chromatogram. And we ultimately get out a hit list. This hit list is ranked in descending order of F ratio. So analytes near the top of the hit list are more likely to be statistically different, while analytes at the bottom of our hit list are less likely to be statistically different between classes. So we can visualize our hit list as this scatter plot, where the x-axis shows the hit number and the y-axis shows the log of a p-value from a t-test. All the dots that you see in orange were statistically different with a p-value less than 0.01, while all the analytes that you see in purple are not statistically different between classes and with a p-value greater than 0.01. So what we can see is that F ratio was really effective in reordering all of our peaks in our chromatograms. So that way, we at the top of our hit list, we have all of those analytes that represent statistically different concentrations between the clean and the strong samples. In total, we found 359 class distinguishing compounds. And also as a really good validation check, the second hit in our hit list was that IPMP molecule that we knew from our targeted analysis study was correlated to potato taste defect. We can visualize these 359 compounds based upon their signal ratio. That signal ratio being what was their signal in all the strong coffee samples and what was their signal in all the clean coffee samples divided by one another. So we can visualize that as the signal ratio plot, where we're basically projecting their signal ratio on a window surrounding each one of the peaks. So if it has a red color, that means that it has a higher abundance in our clean coffee samples, and ultimately that was 327 analytes, while 32 analytes that you would see highlighted in a blue color actually had higher abundance in our stronger potato taste defect sample. So this kind of supports our theory that we saw with those tick chromatograms, where a lot of the analytes kind of dropped out in signal when they moved to the strong potato taste defect samples. But we wanted to take this one step further and kind of see how were the analytes actually correlated to the concentration of IPMP, that known marker of potato taste defect. To do this, we decided to utilize a regression modeling technique known as partial least squares to model the signal from all of our analytes discovered by F ratio and correlated to the property measurements of the concentration of IPMP. So using both this X block and Y block information, we get out two key pieces of information from PLS. The first being the regression plot, which basically highlights that linear dependence of how well our chromatographic signals can correlate to those property measurements, but also the linear regression vector. So this will tell us exactly what type of analytes were positively correlated or negatively correlated with the concentration of IPMP. So first, looking at that regression plot, as I said, this highlights the linear relationship between the measured property values and those predicted by our PLS model using the chromatographic information for all those hits discovered by F ratio. And what we see is that we have this really good correlation between the measured and predicted IPMP concentrations. They're falling pretty much along that 1-to-1 line in black, and we have very low normalized root mean square errors of prediction, approximately 10%. More interesting to look at is actually the linear regression vector. So like I said, this describes how features in the chromograms are related to IPMP. So if you see a box that is highlighted in a blue color, that means that it has a positive linear regression vector loading. So as that peak signal increases, so does the concentration of IPMP. Meanwhile, if you see a box highlighted in a negative in a red color, that means that that analyte has a negative linear regression vector. So therefore, when that peak signal increases, we're actually seeing a decrease in the IPMP concentration. So I projected all those linear regression vector values onto those peak windows surrounding each one of our peaks in our chromatogram. And what's really interesting is that if we compare that linear regression vector from our PLS model on the right-hand side to the projection of the signal ratios that's on the right-hand side, we see they look pretty much the same. So every analyte that had a strong to clean signal ratio greater than 1 was positively correlated with the concentration of IPMP. Meanwhile, every analyte that had a strong to clean signal ratio less than 1, meaning that was higher abundance in the clean samples, was negatively correlated with IPMP. So here we're actually able to say that all these analytes that we discovered from F ratio analysis was not only correlated to potato taste defect in their sensory attribution, but actually the quantitative information of how they relate to IPMP, that known marker of potato taste defect. So using these loadings, we can kind of reorder our hit list and look at the analytes that are most significant for being downregulated in potato taste defect or upregulated in potato taste defect. So first, if we take a look at those that had higher abundance in our clean coffee samples, here I provide a list of some of our compounds. We can look at their sensory descriptions and we see that they have nutty, fruity, and roasted aromas, so those very desirable aromas that you would want in your coffee beans. And if we look at the box and whisker plots for two example analytes, 2,6-dimethylpyrazine and 3-acetyl-2,5-dimethylfuran, we see that they have their highest signal in the clean coffee samples, but then their lowest signal in any of the potato taste defect samples, mild, medium, or strong, and it's relatively invariant in all of those samples. So we can say that potato taste defect directly impacts the aroma associated with roasted coffee beans. Next, if we look at those analytes that were upregulated by potato taste defect, again, I highlight a couple of those analytes. What was really interesting was that none of these analytes really had any big markers in their sensory descriptions. But we can still dig into the literature to kind of figure out some of the significance behind them. So I'm going to highlight two analytes, 2,4-diterpbutylphenol, that's on the top box and whiskers plot, and 1,1,3-trimethyl-3-phenylenedione, that's the bottom box and whiskers plot. What we can see is that they pretty much have no signal in our clean coffee samples, but then they greatly increase in signal when we go to any of our potato taste defected coffee samples. And when we start to dig into the literature, we can actually see that these analytes unveil a potential pathway for causing potato taste defect in these roasted coffee beans. So when we think about how the coffee beans are grown, if this Intestia bug actually feeds upon the coffee fruit, that introduces holes into the coffee beans. That creates favorable conditions for microorganisms such as bacteria and fungi to grow. Due to that microorganism growth, that causes the plant to mediate a stress response, and that increases the amount of chlorogenic acids in the coffee beans and in the plant as a whole. Then, if these coffee beans that were affected by Intestia bug damage end up being roasted, those chlorogenic acids degrade down into phenols and phenylenedions. So this potentially reveals a pathway as to why we saw these increases in phenols and phenylenedions in our roasted coffee beans due to this Intestia bug damage. So in conclusion, we showed that IPMP concentrations were significantly different based upon odor severity of potato taste defect. And due to the power of GC-GCMS and tile-based F-ratio analysis, we discovered 359 analytes that were affected by potato taste defect. And the vast majority of these were higher in our clean coffee samples than our strong coffee samples. Using the F-ratio results, we were able to have accurate predictions of IPMP concentration with PLS regression. And the ordering of those analytes was allowed us to not only say that the volatile profile of these coffee beans was affected by potato taste defect, but also reveal a potential pathway for potato taste defect as well. So with that, I would like to thank you, all of my lab members for their collaboration. I also like to thank the really great collaborators that we have both at the University of Liège and at Seattle University for their help on this project. Thank you guys for your attention. I'll be more than happy to answer any questions.